exponential functions. You'll be able to classify an exponential expression and equations as growth or decay, solve basic exponential equations, and graph exponential functions, including those involving the natural number e. Now, an exponential function is an equation in which the variable is in the exponent. Exponential, variable, and exponent. To solve such functions, you need to first determine a common base that can be used to express both sides of the equation. Then, express both sides of the equation using this common base you've determined. At this point, since the bases are the same, the exponents must be equal. Therefore, you can write an equation to show that the exponents are equal. And then you simply solve that equation. Now, some examples of exponential functions include population growth, compound interest, and radioactive decay. Radioactive decay is used to date ancient objects found at archaeological sites. Here's an example, or two examples, of solving an exponential equation. First, I look at 8 and 16, and I need to think about, do they have a common base? Why, yes, they do. They both have the common base 2. I can rewrite both of them using a base of 2. 8 is 2 cubed, 16 is 2 to the 4th. And then I still have to raise that to the x power. Well, remember, when we raise a power to a power, you multiply. Now that I have 2 cubed is equal to 2 to the 4x, since the bases are the same, I can simply set the exponents equal to one another. That means I have 3 is equal to 4x. Solving that equation is simple. X is equal to 3/4. How about this other one? 6 to the 2x is equal to 1/216th. Well, 6, I really don't have another base to write that in, because it's not 2 to something or 3 to something. 4 and 5 don't go into it evenly. Well, let me think. If you consider that 216 is equal to 6 cubed, and 6 to the negative 1 is equal to 1/6, it would follow that 6 is a common base, and that the way you rewrite it is 6 to the negative 3. The negative puts it as 1/6 cubed. 6 to the negative 3 is equal to 6 to the 2x. Again, I simply, since the bases are now equal, I can set the exponents equal to one another, and I can solve. X equals negative 3/2. I can hear some of you asking, well, what if there's not a common base? What if there's not a common base, we're going to use logarithms. But we haven't learned logarithms yet, so don't worry about it until next time. Right now, everything that I give you when we're doing it when we're solving problems with exponential equations like this, we will be using a common base. Now, in order to do that, you've got to be able to recognize some powers. 36 to the x, that's the same thing as 6 squared to the x, which is equal to 6 to the 2x. Remember, when you raise a power to a power, you multiply. 243 to the 2x. That's actually 3 to the 5th power. 3 to the 5th power to the 2x power is 3 to the 10x. 64 to the x plus 1. Well, 64, if you're not sure about 64, remember that it's 8 squared. But 8 squared can be rewritten as 2 cubed squared. Well, that's just 2 to the 6th. I have 2 to the 6th to the x plus 1. Now, this means that you can write this as 2 to the 6x plus 6, or you could write it as 2 to the 6x plus 1. Either way is perfectly fine. Now, to get a little bit of practice, let me move the recording down here. What I want you to do is rewrite each side so that the base is the same. With the same bases, you can then set the exponents equal to each other and solve for the variable. I'll go through the top row first with you as an example, and then you should try the bottom two rows. Here we have 25 to the x is equal to 5. Well, remember that 25 is 5 squared. 5 squared to the x is 5 to the 2x. 5 can be rewritten as 5 to the 1. I now have 2x equals 1 and x is equal to a half. Think about that. It makes sense. 25 to the 1/2 power. 25 to the 1/2 power is the same thing as the square root of 25, which in fact is 5. The whole thing checks. Okay, 9 to the x is equal to 243. Remember on the previous one, here you could try 9 times 9 times, that didn't work. 9's not a common base. But remember that 9 can be rewritten as 3 squared, and then 243 is 3 to the 5th. Again, common bases. Since the bases are equal, the exponents must be equal. 7 to the x is equal to 1/49. Don't forget about those negative exponents. They'll give you your reciprocals. Here, 7 to the x is equal to 7 to the negative 2. That becomes extremely easy when you remove your common bases. X is just equal to negative 2. Okay, pause the video. You can keep these. I'll keep these right here so you can refer to them. And you have 6 more problems to try. Pause the video and try those problems. Welcome back. Let's see how you did. Did you get to the negative 5 is equal to 1/32? All right. How about 81 and 27? Well, 9 will go into both of them. 9 is not the base. It is 3. Here, you just take everything back down to 3. Now I've got 343 and I have 7. Since I'm telling you that they're going to be common bases and 7 is a prime number, 343 must be able to be rewritten with 7 as the base, and it can. 343 is 7 cubed. Here's the rest of it. I got 3 times 2x because a power raised to a power you multiply. And here's this one. And finally, 1/8 to the x is equal to 2 to the 3x minus 1. 1/8 is 2 to the negative 3. And then you set your exponents equal. How did you do? It's not too bad, is it? Okay, moving on. Here are 4 more problems to try. Pause the video, try them, and then start the video again. Oops. These are problems courtesy of Regents Prep. Did you get negative 7? Now this one's interesting. Here, I brought it down to 3. Do you have to bring it down to 3? No. I could leave it as 9 to the 3x. And then on the other side, I could do 9 to the 2 and the x minus 4. This would give me 3x is equal to 2x minus 8. I subtract the 2x from both sides, and x is equal to negative 8. Notice, same answer, same answer. So this one, it wouldn't matter if you wanted to use the base of 3 or the base of 9. That said, be careful here. 8 is not a base of 16. 4 is not a base of 8. Both of these have to be taken to 2. Okay? You can't raise 8 to an integral power and get 16. You can't raise 4 to an integral power and get 8. And over here. So far, so good? How about so far, so easy? Graphing, yay! Woo! Yay! We've got to do graphing. All right, so the domain is the set of all real numbers. The range is the set of positive real numbers. This is for the parent function. The y-intercept of the graph is 1. How would this change? If you move the parent function up and down. The x-axis is an asymptote of the graph. It's a horizontal asymptote. Now remember, anything to the 0 power is 1, so whatever your base is, that base to the 0 power is 1, and that b to the 1 is b. So here you can get 2 points. You know you've got your asymptote, and it just increases exponentially. Now remember, if I multiply by something, such as this a here, okay, this a is my vertical stretch or compress. It's my vertical stretch or my vertical compress of this graph. Now, let's take a look at some of these. I'm not going to get real crazy with it because you've done all this before and it's the same process. Whatever the base is, that's your base. And then you can grow or you can decay. Growth is when the base is greater than 1. Decay is when the base is between 0 and 1. Here's a graph. Exponential, it's increasing. This is an increasing exponential growth. When it's decreasing, such as the green one, that's called exponential decay. Note, a base greater than 1 raised to a negative exponent would be decay because that negative exponent would put it 1 over. Now, let's take a quick look at some graphs of exponential functions and focus on the basic shape and the transformations that occur. I'm going to use 2x because it just keeps the values small. Y equals 2x. 2 is going to be our standard base for this parent function. 2 to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the negative 1 is 1/2. I've got some points and I can graph. If I put a negative in front of my base, notice it's a reflection over the x-axis. It's what it's always been. I reflected over the x-axis, so instead of moving left to right up, I move left to right down, and I'm below the x-axis. Now, if I multiply it by something in front, here's my stretch factor, I get a vertical stretch, or it could be a vertical compress if I wanted to make it more shallow. Notice at 1, 1 times 1 is 5. 2 times 5 is 10. Here, where it's 4, 4 times 5, this will be way up here at 20. When you have the number out front, you're multiplying it over here by the y values. So you take your parent function, multiply the y's by that stretch factor, and you get the y value. Now, horizontal shifts. If you're shifting it horizontally, you're going to add or subtract to the exponent. Notice, here's my x minus 3. I shifted everything right 3. I can even take this guy and 1, 2, 3. Here at 1/2, 1, 2, 3. Okay. 2 cubed was up here at 8. 1, 2, 3. I have my new curve shifted to the right. Remember, when it's x minus, then whatever the number is that's being subtracted, in this case 3, that's what I add to my x coordinate to get my new point. Horizontal shift right. Vertical shift is when you add after you've done the exponentiation. So 2 to the x plus 3, where the plus 3 is on the same level with the base, right? I move it up 3. So here I was at 1, 1, 2, 3, 1, 2, 3. If I come up here to 4, 1, 2, 3. Up here at 8, 1, 2, 3. And notice I have my asymptote running right along here. My asymptote went from being y equals 0 to y is equal to 3. It raised up 3 units. Why? Because I took the entire graph and shifted it up 3 units, so the asymptote also shifts up. Important. Remember, if the asymptote is not on the x-axis, then you need to draw it in with a dashed line. Here's a decreasing function. Okay? 2, I change it to 1/2. Remember that 2 to the negative 1 is equal to 1/2. So this could just as easily be, I think this blue, y equals 2 to the negative x. Remember, a negative up there, or inside the parentheses, I would reflect it over the y-axis. The blue curve is a reflection of the parent function, y equals 2x, over the y-axis. Now, a decreasing function, you can flip it over the y-axis and then drop it too. Again, notice here, I have included my asymptote. My asymptote is a horizontal line at y equals negative 2. And then I took all of my points and I moved them down 2. I can even take this guy and moved him down 2. Introducing E. Okay, in class, we'll watch this YouTube video. If you'd like to watch it now, you can certainly copy down the URL and click on it. But since this is really just an online lesson to make sure that you get the basics and get the instruction you missed in class, I'm going to continue on. Natural base E. The natural base E is irrational, just like pi, just like the square root of 2. It is defined as, mathematically, as n approaches infinity, 1 plus 1 over n to the nth approaches 2.718281828459 on and on and on. E is used in many applications, including the estimation of the ages of artifacts found at archaeological digs and the computation of interest when it's compounded continuously. You're going to treat E like any other real number. Basically, you can treat E like pi. It is nothing more than a mathematical constant. Now, when you think about E, remember how once we had imaginary unit and imaginary numbers, we did not play around with using I as a variable. Good idea not to use E as a variable now because E is actually a number. So, taking a look at this, pause the video and see if you can answer these. Remember, E is a real number. It just happens to be irrational. All right, did you remember when you multiply like bases? You add the exponents. When you divide like bases, you subtract the exponents, but don't forget, 6 divided by 2 is still 3. You're not subtracting the 2 from the 6, you're dividing the 6 by 2. Be careful. This next one over here, you're multiplying, you're raising every single term for every single variable and number to the second power. So negative 4 times negative 4 is 16. E to the 3x squared, multiply the exponents. Here I'm adding my exponents and I just get E. This one takes a couple of steps. Hopefully you did them. First, I raise the numerator to the third power, and then I take care of dividing. I divide negative 27 by negative 9 to get the 3, and then I subtract 7 from 12. So now I have e to the 5th. Evaluating natural-based expressions. For this, you need to use your calculator. I'm going to pause for just a moment so I can go and find my calculator. Okay, with your calculator, to evaluate e to the negative 3. Right here on your calculator, right above natural log, ln is the natural log, is e to the x. So you're going to press e, oops, sorry, I'm going to clear that. Second natural log will give me e to the x, and then I can just type in negative 3, and boom, I've got my answer. Oops, let's see if I can keep this here. Right, notice 0.0497, that's approximately 0.50. E, second natural log, to the 0.7, well, that's 2.01375 or 2.014. Go ahead and you try the next few. See if you don't get these answers. And don't forget, it's second, then you come down here to natural log, here's your e to the x, and you'll wind up with e raised to a power. If you've got an older calculator, it might just come up with e, in which case you need to use the caret key over here. Press the up arrow and then put in the exponent. This should be fairly simple. Just want to make sure you know where everything is on the calculator. Okay, graphing the natural base, same thing. Here we have 3e to the 0.4x. I've stretched it by 3, a horizontal stretch of 10/4. Okay. At 0, if I put in a 0, anything to the 0 is 1 times 3 is 3. E to the 1, and then multiply that by 0.4. You actually get 4.48. So I can plot a second point. I know, just like any other number, it's going to be asymptotic down here to the x-axis. It's really not that bad, I promise. Okay, remember you have y equals a times e raised to the plus or minus x minus h plus k. H shifts us left, right. H is our left, right. K is our up, down. A is our vertical stretch or vertical compress. This plus minus is reflect over the y, and then a plus minus out front here. This is your reflection over the x. If the exponent is positive, you have growth. If the exponent is negative, you have decay. The general shape of the graph, there's exponential growth. Exponential decay is going to come down and then level out. Here are a couple of graphs. Again, notice, moving left 3, down 2. Important thing, when I move down 2, I'm going to need my horizontal asymptote. My horizontal asymptote is down here too. I just take each one of these points and I move them left 3 and down 2. Oops, let's come back up here. Left 3, h is negative 3, down 2. Here, I just take the whole graph and I move it up 1. Quick look at an application. Continuously compounding interest, there's a formula called PERT. A equals P-E-R-T. PERT. Okay. A is your amount in the future. P is the principal or the amount that you have today. R and T, R is the rate at which the interest is, and T is the time. You use the base of E when you're compounding continuously. So you deposit $1,400 in an account that pays 4% annual interest, compounded continuously. What is the balance after 1 year? Just plug things in. Okay, you plug in, you don't know what the future is, but you do know you deposited $1,400 for 1 year. The T, the time, is in years. So you wind up with $1,457.14 at the end of a year. Now, what if you deposit $800 into an account that pays 9% annual interest compounded continuously? What is the balance after 3 years? Okay, well here, your T is equal to 3, your P is equal to 800, and your rate is 0.09. You have everything you need to plug in. Plug the values in and get your answer. Good job. Now, just the summary. Whew. Almost there. Almost. Exponential functions are of the form y equals a b to the x minus h plus k, where b is greater than 0 and b does not equal 1, because 1 to any power is just 1. The domain of exponential functions is all real numbers. The range is y greater than k, unless it's been reflected over the x. If 0 is less than b is less than 1, the function is a decreasing function and has the following general shape. In this case, we call it decay. Likewise, if b is greater than 1, then the function is considered to be increasing. It has this general shape. The y-intercept of b to the x is 1. The only way to change that is to move it up or down. Goodness. The graph of the x of the parent function y equals b to the x does not intersect the x-axis. There is no x-intercept. The line y equals 0 is the horizontal asymptote. If there is a vertical shift, it's y equals k. Exponential functions are continuous. To solve basic exponential functions, you determine like bases, rewrite the function using like bases, set the exponents equal, and solve for the variable. Are we done yet? Yes. Whew. We're done with this lesson.